Hello, this is Bijna Miss. We will start with our first chapter in class 12, which is Electric Charges and Fields. I have already sent the notes through WhatsApp and I hope you have all got it in front of you. If you look at the first page, you will see that I have listed three properties of the first topic itself is the basic properties of electric charges. There are three properties. I have listed all of them there. The first one is additivity of charges. Additivity of charges would mean that if you have a body which has a number of charges, for example, it has charges Q1, Q2, Q3 and so on, then naturally the net charge or the total charge on that body is going to be the algebraic sum of these charges, that is Q1 plus Q2 plus Q3 and so on. That is the total charge on the body will be the algebraic sum of these all these charges together. That's the first property. We then have the next property which I have written there is the conservation of charge. Conservation of charges simply mean that you cannot create new charges nor can you destroy these charges. You can transfer charges from one body to another body, but they will always be conserved. That means the total charge will be always a constant. For example, if you take a glass rod and rub it with a silk cloth, then because of the friction, the glass rod will lose a few electrons, but the silk cloth will gain those electrons. So the number of electrons lost by the glass rod will be equal to the number of electrons gained by the silk cloth. So this is what you mean by conservation of charges. So what will happen? The glass rod which has lost the electrons will become positively charged. The silk cloth which has gained those electrons will become negatively charged, but the net charge will always remain as constant. And that's what you mean by that second property, conservation of charges. The third property, you will see what I've written there is quantization of charge. As you all know, I hope all of you know that electronic charge represented by E is equal to 1.6 into 10 raised to minus 19 Coulomb. Now, if you take any charged body, the total charge in that body has to be an integral multiple of the Z. That means the net charge or the total charge on any charged body will be an integral multiple of this electronic charge, that is Q equal to NE, N being any integer. So these are the properties of the basic properties of electric charges. We have discussed three of them: additivity of charges, the second one is conservation of charges, and the third one being quantization of charges. Okay. We now go on to the next topic, that is Coulomb's law. Last year in 11th standard, you have learned gravitational law, where it's called the inverse square law. I hope you remember that. If you have two masses, let's say mass m1 and another mass is m2, the two are separated by a distance r, in which case the gravitational force that exists between the two is g m1 m2 by r square, where m1 and m2 are the two masses. So this force, gravitational force, is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. And so it's called the inverse square law. It's the same thing, and G is a universal gravitational constant. Now the same thing this year is the electrostatic force, where we are talking about two charges Q1 and Q2 separated by a distance r. So this force F, as you know, if both are positive, is going to be like charges, it will be repulsive. Unlike charges, it is going to be attractive. And this force is directly proportional to product of the two charges Q1 and Q2 and inversely proportional to the square of the distance between them, r being the distance between them. Now if you change this to an equality sign, the constant of proportionality in electrostatics is 1 by 4 pi epsilon 0 Q1 Q2 by r square. Here this 1 by 4 pi epsilon 0 is a constant whose value is this 1 by 4 pi epsilon 0 has got a constant value 9 into 10 raised to 9, where in that this epsilon 0 is called the permittivity of free space or vacuum. Permittivity is the capability of a medium to allow free lines to pass through it. So for air or vacuum, this epsilon 0 value is, so I hope you've noted this in your printed notes, it is there. Force is directly proportional to product of the two charges and inversely proportional to the square of the distance between them. We are now discussing about this constant here. This constant in electrostatics is 1 by 4 pi epsilon 0, whose value is 9 into 10 raised to 9. And in that we have this epsilon 0, which is called the permittivity of free space. Its value is 8.85 into 10 raised to minus 12 Coulomb square Newton per meter square, meter raised to minus 2. So we have 8.85 into 10 raised to minus 12 Coulomb square Newton raised to minus 1 meter raised to minus 2. That's the SI unit of this permittivity. So that is Coulomb's law. So you clearly now understand why Coulomb's law is called the inverse square law, because it is directly proportional to the square, to the product of the two charges, but is inversely proportional to the square of the distance between them. So that means if the two charges are taken far apart, then the force will go on decreasing. If you bring them closer, the force between them will go on increasing. Now if you look at your first page, the last topic that I've printed there is the electric field. Let me now explain to you what we mean by an electric field. Now suppose I keep a positive charge. Let's say I'm going to keep a positive charge, let's say plus Q. I'm going to call it a source charge, this plus Q. And if I take a plus 1 Coulomb and keep it at a distance R, this plus Q here is called the source charge. This plus 1 Coulomb here is called the test charge. A test charge is always a unit positive charge, 1 Coulomb, plus 1 Coulomb. And I'm going to keep this unit charge at a distance R from the source charge. So we know force is then given by 1 by 4 pi epsilon 0, Q1, Q2. Q1 has become Q, Q2 has become 1 Coulomb. So Q into 1 divided by R square. This is what you call as an electric field. So electric field from here you would have understood is a force experienced by a unit positive charge when it is kept at a distance R from the source charge. So that's why your formula for electric field is now 1 by 4 pi epsilon 0 Q by R square, because the second charge we are talking about a unit positive charge. This electric field, just like force, has a direction given, and so it is a vector because it has a magnitude as well as a direction. So I'll repeat, electric field is now defined as whatever force is experienced by a unit positive charge called the test charge when placed at a distance R from any source charge. Formula will therefore become 1 by 4 pi epsilon 0, that's a magnitude, Q by R square, because we have replaced the second charge with unit charge, unit positive charge. We now, if you turn over the page, you will see that the next thing we are talking about is electric field lines. Electric field lines. Okay, electric field lines. We have, let's say we have a positive Q is our source charge, and like before I'm going to keep a plus 1 Coulomb here. We know that the force experienced by this unit positive charge is what we call as electric field due to the source charge Q, and it is given, its magnitude is given by the formula 1 by 4 pi epsilon 0 Q by R square. But I told you this electric field is a vector because it's a force and it must have a direction. So we are now discussing the direction. So if I keep a plus 1 Coulomb here, and because this is also positive, there must be a repulsion. So naturally this plus 1 Coulomb is going to be repelled, and this arrow mark shows you the direction in which that 1 Coulomb is going to experience a force. If I keep that 1 Coulomb here, then naturally this source charge is going to repel it. So you will see that this source charge is going to repel that 1 Coulomb, radially away from it, and the lines that I've drawn here actually represent the direction in which this plus 1 Coulomb placed around the source charge will experience a force, the direction. So electric field lines are actually imaginary lines which are drawn, and they are drawn to represent the direction in which a unit positive charge will experience a force due to this plus Q, the source charge. So you will see the electric field lines definitely have to be radially away from the positive source charge. If you replace this source charge by a negative source charge, then what will happen is all these field lines will now be radially inward, simply because if you keep a plus 1 Coulomb here, this plus 1 and minus 1 both are unlike. So naturally what the source charge is going to do is it will attract the plus 1 Coulomb towards it. So wherever you keep your plus 1 Coulomb in the vicinity of the source charge, that plus 1 Coulomb is going to be attracted by the source charge, and therefore you will see that if your source charge is a negative charge, then the field lines will be radially inward. So we have just seen the direction of electric field lines in the case of a positive source charge and in the case of a negative source charge. So I hope you've understood very clearly that these electric field lines are imaginary lines which simply represent the direction in which that plus 1 Coulomb can experience a force when it is kept near a source charge. Positive source charge would mean they are radially away. Negative source charge would mean they are radially towards that source charge. We also have another case where we have a positive and a negative charge, a positive charge Q and a negative charge Q placed like this. Naturally, the electric field line, the imaginary line, will be in a direction from the positive to the negative, because if you keep a plus 1 Coulomb here, it will be repelled. This plus 1 will be repelled by the plus Q but attracted by the minus Q. So naturally, plus 1 Coulomb is going to be pushed away from the positive Q and towards the negative Q. So electric field lines will be always directed from the positive to the negative. And these are the electric field lines that we have represented here. For source charges which are plus Q, it is radially away. For source charges that are minus Q, it will be radially towards the negative charge. And from positive to negative always, electric field lines. Properties of electric field lines, I've already jotted it down for you in your printed notes. I think you need to just go through it. Whatever we have done here, the explanations are there in your printed notes. So please go through that. There is one more definition for electric field which we need to learn before we go into the next topic, that is the electric flux. Now, I told you just now that electric field always, these field lines are drawn from positive to negative. You understood why? Because naturally a plus 1 Coulomb is going to be repelled away from the positive source charge and going to be attracted towards the negative source charge. So electric field lines always will pass from positive to negative. Let us imagine here we have a plate, a conductor, which is positively charged. And I also keep another conductor here, which is negatively charged. Naturally, we have field lines which are passing from positive to negative. These are the field lines that I am representing. Now, when we have field lines like this, the number of field lines that pass through unit area is also called an electric field. For example, you can see that I have a piece of paper here and I have marked a unit area here. Can you see there's a small square here that I've drawn? Let's say this is 1 meter breadth and 1 meter length. So this portion that I've drawn here is a total area of 1 meter square, 1 square meter. And I've put some dots in that. I have put 1, 2, 3, 4 into 4, 16 dots there. These dots actually represent field lines. For example, Suppose I have field lines. Let's say this is positive and this is negative. So your field lines are passing from positive to negative, and I go and keep an area which is like this, perpendicular to the field lines. Your field lines are passing like this, perpendicular to this area. The number of field lines that will pass through this unit area, here I have put 16 dots. All 16 dots represent field lines that are perpendicular to that area. Those number of field lines passing perpendicular to unit area is what you call as electric field. So we have two definitions for electric field now. One, previously we learnt that electric field can be defined as the force experienced by unit charge when it is kept at a distance r from a source charge. Right now I told you that if you have field lines passing from this positive plate to this negative plate, and I go and keep a area that is an area like this which is perpendicular to the field. If your field lines are passing like this, I kept this area perpendicular to the field lines. The number of field lines passing perpendicular to unit area is what you call as the electric field. So we have two definitions for electric field now. So after the definition for the two definitions for electric field, I would also now like to introduce the SI unit for electric field. You know that F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. The same F becomes electric field 1 by 4 pi epsilon 0 if you replace the first charge by the source charge and the second charge by unit charge, and so this is Q by R square. So if you look at the relation between these two, you may write F is equal to Q times E. That means, what is electric field? Electric field is force experienced by unit charge. If you have Q charge, then the force experienced becomes Q times that electric field. Because naturally electric field means what? Force experienced by a single positive charge, unit charge. If you keep Q charges, let's say you kept 10, then the total force will become 10 times the electric field. So F is equal to Q times E, or you will see that E equal to F by Q. SI unit for F is Newton and for Q it is Coulomb. So you will see that the SI unit of electric field is Newton per Coulomb. I'll repeat it once more. You have electric field is what? Force experienced by unit positive charge. If you have Q charges, then the total force becomes F is equal to Q times E. From here you will see the electric field is equal to the electric field is equal to F by Q, and F is in Newton, charge is in Coulomb. So we have the SI unit for electric field as Newton per Coulomb. I hope the whole thing about this electric field is clear to you. All you need to know is electric field is a vector quantity. It has a direction. Electric field has two definitions. Its magnitude is given by 1 by 4 pi epsilon 0 Q by R square. The relation between total force and electric field I have written here, F equal to Q times E. Its SI unit is Newton per Coulomb. This is all you need to know on electric field. If you look at page 3, you will see that the next topic is electric flux, denoted by phi. Phi as in like this. Phi, electric flux phi. Electric flux is phi. Now, let me first explain to you what you mean by this electric flux before we go into the formula and all that. I just told you that if I take an area like this, the number of field lines passing through unit area is what you call as electric field. If you notice, I have put 16 dots here. Each dot represents an electric field line passing perpendicular to this area, and this area I told you is 1 meter square. So, electric field lines is a number of field lines. Electric field defined as a number of field lines passing perpendicular through unit area. Now, I have taken a larger area. So, naturally, if you have an electric field like this, there will be electric field lines passing perpendicular through this whole area. The total number of field lines passing perpendicular to this whole area is what you call as electric flux. Area in our textbook, NCERT textbook, is denoted by delta S. Till 11th standard, area is denoted by delta S in the NCERT textbook. Now till 11th standard, we have learned area is a scalar quantity. It doesn't have a direction, only has a magnitude. But you will see in this particular case where we are dealing with electric fields, the direction in which you keep the area does matter. For example, if your electric field lines are, let's say, passing like this, there's a positive plate here and there's a negative plate here. So electric field lines are passing from positive to negative. If I keep my area like this, you will see maximum number of field lines will pass perpendicular through this area. And on the other hand, if I place my area like this, your electric field lines are passing like this. There are no electric field lines passing perpendicular to this area. So how I keep the area does matter. Then the flux will depend on the direction of the area. If your electric field lines are passing like this and I keep my area like this, then maximum number of field lines will go perpendicular to the area. But if I keep it like this, all your field lines are going to pass like this. None of them are going to pass perpendicular to the area. So the electric flux would have reduced to zero. Let me make it a little more clear to you. Suppose we have a positive plate on top and we have a negative plate down. So field lines, electric field lines will pass from positive to negative. So we have a downward electric field like this. If I keep my area like this, maximum number of field lines will pass perpendicular to this area. But if I keep my area like this, then no field lines are passing like this. All field lines are going down. There are no field lines perpendicular to the area. So electric flux will become zero. So I hope you've understood that now area cannot remain a scalar quantity. It has to become a vector quantity, because how you keep the area, the direction of the area will determine the flux. So therefore, area is going to be a vector in which the direction of that area vector written as delta S with a vector sign on top. Direction is going to be always perpendicular to the area and outwards. For example, if I keep it like this, then the area vector is perpendicular and outwards like this. If I keep my area like this, then the area vector is going to be perpendicular and outwards like this. So area is going to be a vector now in these cases, and area does have a direction. The direction of that vector quantity is always perpendicular to the area and outwards. So now we can go into flux. Flux, I told you, is the number of field lines that pass perpendicular through the whole area, not just unit area, but the whole area. And if the whole area I am denoting as delta S, then it will be the flux phi is equal to E dot delta S, where both E and delta S are now vector quantities, and we take the dot product. We take the dot product here. I think this is very simple for you to understand, because how did we define electric field to be? We defined electric field to be the number of field lines passing perpendicular through unit area. If you multiply it with the total area, obviously you're going to get the total number of field lines passing perpendicular through that given area delta S. So that is what you mean by flux. And because it is a dot product, this flux becomes a scalar quantity. So because dot product, we may write E delta S cos theta, theta being the angle between the two vectors, one vector being the electric field and the other vector being the area vector. So let me just give you an example. Suppose we have a electric field that is downwards. Okay, we have a positive plate on top, we have a negative plate down, and your electric field lines are directed from the positive to the negative. And I am now going to keep my area vector like this. Now the angle between. So if you look at the electric field,